think we're live. All right. Hello, everyone. Welcome to Quirkcast. I am your host, Tim.
Now, Mikey.
Right. So,
Welcome.
Yeah, welcome to our episode. So, unfortunately, Sahil couldn't make it. So, we will try our best to fill in the gaps for Sahil. So, hopefully, our discussion won't be too technical. And feel free to leave any questions in the comments. And if you haven't done so already, do join our Discord channel. So, let's get started. So, Mikey, yeah, last time I think we talked about whether or not physics is exact. I mean, and for those who are not familiar, why don't we do a little bit of recap? Like, why is that even a problem in the first place? And what's the big deal with, who cares if physics is exact or not? Why is that even a problem?
Yeah, right. So I guess, just to recap, we talked about previously about how, right, like if you calculate some quantity that's like a real number, let's say I try to measure the value of pi. I try to measure the ratio of a circumference to the radius of a circle. There's an experimental error here. So, like, no matter how accurate my measuring instruments are, if I measure the ratio of a circumference to the diameter of a circle, I'm not going to get exactly 3.14151. I'm going to get something that's a little bit off, right? So this is what we're really talking about here. Like, there's kind of two parts. Like, can we ever measure something to be perfectly accurate, and can we ever calculate anything to be perfectly accurate? It seems like there's always some limitation, either experimental or theoretical, that prevents us from getting what we call an exact answer, the exact truth.
Yeah, and I guess we can reiterate that this actually isn't a physics specific problem, yeah, because it seems like, I mean, of course, everything is physics, but even I'm glad that you bring out this example of pi. Like, we don't know the digits of pi through infinite precision. There's always, even inside of a computer, when you see 3.1415926, like, it's doing a calculation to try to approximate that, right? So, but I guess the question is, sure, we can all understand that physics isn't exact, but what are there problems beyond that? Just that it's not precise.
Yeah, I mean, I think computers are a good example, right? Like, so yeah, if you open up your Python program and you type numpy.py, you're going to get some number 3.1415. But if you go all the way to the end, it's not going to be exactly pi, right? So even your computer is struggling to find something close to the solution and doesn't hope to find the exact solution. So in all problems in engineering, this is an issue. It seems like there is something called the exact truth out there, and we're trying to touch it, but we can't touch it exactly, and so we get closer and closer and closer and closer to it incrementally.
Yeah, and also we mentioned something about what we call perturbation theory, right? So maybe we can recap some of that. How is that used in physics?
Yeah, I mean, I don't know. In my mind, perturbation theory, for those people who've taken, high school calculus, it's just the idea of a Taylor series. We went over this last time, right? Like, so if you're trying to express the number 2, there's a couple ways to do it. You can express 2 as 1 plus 1. You can express 2 as 0 plus 2. Another way to express the number 2 is you take the number 1 and you add a half, and then you add a fourth, and then you add a 16th. And if you do this infinite number of times, you'll eventually get something that approaches the number 2. So 1 plus a half plus a fourth plus a 16th. It's the famous geometric series 1 over n squared. If you sum this to infinity, you'll eventually get the number 2. So there's many different ways to write the number 2, some of which are exact, like 1 plus 1, and then some of which we can express as this infinite series.
Right. But I think there's sort of a bigger problem here. It's that, for the example of 2, 1 plus a half plus a fourth, if you enter the calculator, it sort of makes sense, the digits get closer and closer to 2. But the issue in physics is that sometimes actually you might get the wrong answer, right? Like, instead of trying to get at 2, we might get 1 plus 3 minus 4 plus 7 minus 8, and it just goes crazy. I think we went over some examples, and this is not particle physics specific. They're actually examples in many different systems. Like we talk about tornadoes for a little bit. Maybe we can reiterate some of that analogy and dig deeper into the issue with perturbation theory in general.
Yeah, right. So what is perturbation theory, right? Perturbation theory is like, we know that there's some kind of truth out there that we're trying to touch, but we can't. It's difficult to access it directly. So we try to probe our surroundings a little bit, right? Like, so suppose we want to know what physics looks like when we increase the temperature. One thing we can do is we can take the physics that we understand right now at low temperature and just increase the temperature a little bit and see how the theory reacts. So we sort of explore physics in this kind of piecemeal way by exploring close to our surroundings. And that gives us access to some part of the theory, right? Like, so now we understand how the physics works when the temperature is low. But when we try to go too far away from the environments that are familiar to us, our ability to predict might go away.
Yeah, I guess for the weather analogy, we mentioned something like tornadoes. Basically, the point is that I mean, I guess the analogy is it's kind of like going on a short hike. You can take a small step in each one of the directions. The views will change a little bit, but at some point, you might hit some obstacle. There might be cliffs that you can't go over. There might be deep, gorgeous valleys or peaks that you cannot go over by just taking a small step. And I guess in the weather system, a tornado is one of those examples, right? I'm not too familiar with it, and Mikey, could you explain a little bit about? You're a little bit more familiar. You study a little bit of that.
Yeah. So right, like, so tornadoes are a funny phenomenon, right? Because like when we think about weather, we think of like, clouds, like molecules of hydrogen and oxygen in the atmosphere colliding, organizing, and pretty much when we look at weather, the behavior is pretty random. It's pretty chaotic. Well, under certain circumstances, you can have organized structures appearing, like a tornado, right? Like a tornado is a very simple object to describe from a physics perspective. And it's weird because even though the tornado is like, it's just a simple object, it's a tube, it comes out of this really chaotic environment. And it's very difficult to predict when a tornado is going to form because this is a part of the theory that we just don't have access to.
It seems like part of the issue is like part of. I think we can safely say that whenever a system is chaotic, I think perturbation, this idea of you can just perturb the system a little bit and then see that it changes a little bit, I think it completely breaks down. Would you agree with that?
Yeah, absolutely. Yeah, definitely. Yeah.
Yeah, and
So
the
the problem is that the universe we live in is a peaceful universe, and we try to build our physics in terms of our understanding of how things work when the environment is peaceful. And you can kind of think about this. We kind of talked about this last week. It's like an extrapolation, right? Like we take the physics of the world that we understand right now, and we try to extrapolate it into areas like what happens inside of a black hole. We can't climb inside of a black hole, but we can take the laws of physics that we know, and we can apply them in certain situations and see how it behaves. But when we try to apply the situation, when we try to apply physics to a situation that is very different from the world that we know, the extrapolation basically breaks down. And yeah.
So basically, I guess there are some. I think when we think about it, there are sort of these metaphorical barriers, right? That you just couldn't you couldn't just perturb the system a little bit and see what happens because there are drastic changes. I guess black hole is a good example too. Like you try to probe the black hole, but you take one step smaller than the one before, but the moment you cross the event horizon, everything changes. So it's not. It's not just a perturbation anymore. Okay, so this is roughly kind of our where our episode roughly ends last time.
Wait. Let me just give one more analogy. Like, I don't know.
Yeah,
I kind of like the mountain analogy, right? Like,
yeah.
imagine you're trying to map the surface of a mountain in terms of like where you can go by walking. So I'm on a stable point of the mountain. I can kind of
Mm.
like create a map. I can walk forward. I can walk left. I can walk right. I can walk backwards. And I can sort of like map this terrain. But there might be certain parts of the mountain where there's just like, as you mentioned, there's just a cliff. There's a steep drop off. And then my attempt to map this with my steps doesn't apply there because you can't step over a cliff. So this is the way we kind of try to build up physics. We start from where we know and we try to build up around. We try to build up our immediate environment and try to get a lay of the land in that way. But there are when you do this, you inevitably encounter problems where this approach just doesn't work.
Yeah, I think this reminds me of another episode that we did, and to our viewers, please do check it out. We did another episode of the space of theories, so I think this analogy of
Yeah,
hiking is
absolutely.
quite apt. The exploration that we're doing is literally in the space of theory. We're hiking around in the almost like a map of the theory space, and we take a small step left and right, up and down using perturbation theory. Sometimes we inevitably we hit these obstacles. Kind of we that perturbation theory doesn't work anymore.
Yeah.
Now,
Eventually, you'll hit a volcano where lava's spewing out, and you don't know what that even means.
so I guess coming to our next point, then what? Let's say we hit one of these obstacles. What
Yeah.
what can we do about it? I mean, we talk about some of these potential solutions. Like physics doesn't just stop. Clearly, like we have
Yeah.
tornadoes. We have these interesting phenomenon. What's next? What do we do?
Yeah. So, like, I mean, it seems to me like it's, there's no protocol for doing this. Like, you come across this obstacle to your understanding and you don't know how to get around it. I mean, that's kind of the situation that we're in right now. And it's just pure human creativity and genius to try to find a way to get an answer out of it. Like, we have this approach, which we've been calling perturbation theory, which is the idea of kind of extrapolating from our current environment to try to understand what physics looks like. And as Tim mentioned, we inevitably reach points where this fails. And so what's required here is what often happens. I mean, the most famous examples is people just come up with completely radically different ideas for how to describe these new phenomenon and then try to connect it to this approach that we come to know and love called perturbation theory.
I guess metaphorically speaking, we're literally like building bridges, ladders to kind of
Yeah.
jump over these obstacles, right?
Yeah, trying to find a connection.
So I know that we did mention something about topology. Why don't we
Yes.
go into that a little bit? So it seems like, for those who don't understand, we're gonna describe a little bit what topology is. It seems like that direction is a way to bridge these
Yeah.
different obstacles. Yeah, Mikey, can
Thank
you?
you, Edwin.
Yeah, can you give us some historical context on what the hell that is and like?
Well, I would say like, right, so like we mentioned before, like if you're trying to measure the number pi, you're never going to get it exact, right? Your measuring tools are going to be wrong. And, you might have some analytical methods for actually calculating pi, but you're going to have to resort to some kind of approximation. And this is going to happen anytime you deal with real numbers. But if you figure out a way to turn your problem into a counting problem that only deals with integers, then we get into the realm of where you can talk about, perhaps having an exact answer, right? If I'm trying to calculate something that's 3.1415, I'm never going to get exactly the right answer. But if I'm trying to
Mm.
calculate something whose answer is 3, then I get the answer 3, then that's exact. So trying to approach the problem from the perspective of integers is one way to try to get exact answers from physics.
Do you know some examples, like historically, when do people start looking for these integers and where do they even come up?
Honestly, I think Ed Witten just is a genius and just
Yeah,
thought that this was the way.
I don't know if he's the first though. I mean, he did win a Fields Medal. Just a little bit of context. Edwin, I think, is the only physicist who won the most prestigious awards in mathematics, the Fields Medal, and that was in his work on using the tools of quantum field theory to understand things about topology, which is, as Mikey was saying, a really glorified way of counting different kinds of integer, basically. But I think topology is kind of a complicated subject. Can we
It's not
break
that
that down a
complicated.
bit?
It's the simplest, right?
Why don't you give us some examples? I mean, I think I struggle to come up with.
Well, the classic example is right, like the rope around the tree.
Okay.
So topology deals with so we imagine, as we mentioned in some previous episodes, the way we describe particles, matter, and energy is through fields. There's a field that permeates all of space. And we assume that this field is continuous, that the value doesn't change that much from one point to another. And if you make this assumption that all matter and energy is created by this continuous field, um, it can't have jagged jumps in it, right? Like you can't, in physics, we don't encounter a situation where something just suddenly, well, I mean we do, but in phase transitions, but generally speaking, when the energy is low, yeah, we assume the field is continuous, and so there's this famous result in topology that if I take a rope and I wrap it around a tree once, versus let's say I wrap it around the tree twice, there's no way to go from wrapping around the tree once to wrapping around the tree twice without cutting the rope. Um, so I mean, Ed Witten obviously wasn't the first to discover this, but he was the first person to kind of realize that this could apply to physics, that this principle of like winding number, that there's an integer number of times you can wind a rope around a tree, that this can be used to describe a lot of phenomena in physics. Like you can imagine like counting numbers of particles by, if there's 3 particles, that means that the rope winds around the tree 3 times. And you can't just suddenly go from 3 particles to 2 particles because that would require cutting the rope and
Right.
unwinding.
So I guess we can be a little explicit. So there are theoretical models where the energy of a system is literally some sort of winding number, right? I think, and
Yeah.
that's fair. So
Yeah.
and I think I want to emphasize that this this is an example of a topological, some kind of topological index, let's say. And the reason why this goes beyond perturbation theory is precisely this fact that if you just wiggle your rope a little bit, the winding number cannot change.
Yeah.
So you cannot say, hey, I'm gonna take a system with where the rope winds the tree twice. You cannot take that system and perturb it by jiggling it to get to a system that has winding number 3. So I think I don't know when, historically, when that happened, but physicists
70s?
start 70s, is that right?
Yeah. I think so. 80s.
Yeah. Yeah, I think physicists start to realize that if physics involves things that are topological, you cannot use perturbation theory to study them because you just cannot go from one winding number to another, for example. Right? Are there more examples? I think winding number, a rope around a tree is interesting, but
Well, it's interesting because like you mentioned, I totally forgot that point, but like you can have a theory of winding number 1, and you can do perturbation theory on that theory, right? You can imagine stretching the rope that's wound around the tree once, and you can imagine doing the same thing on the rope that's wound around the tree twice. So there is this interconnected interplay between these integer solutions and the perturbation theory also.
Yeah, and I think in terms of the space of theories, if you think about it, the space of theories, that really means that if you really take this metaphor literally, the space of theories has different islands, basically.
Yeah.
One of them might be winding number equals 1. One of them might be winding number equals 2. And you can't really go from one to another unless you, I don't know, take a boat ride or like a plane flight, like something dramatic, right? I think.
Yeah. Well, you have to cut the rope.
Well, cutting the rope
Yeah.
here means, I guess you have to do something drastic. I guess if you're
Yeah.
climbing a mountain.
Extreme, your field has to be extremely violent.
Okay, but can we give us a maybe an example that's a little more realistic? Like, how does that have to do with particle physics, right? The Rinding numbers, or some other.
Um, yeah.
Well, I think string theory actually literally uses that. You know, like you can
Yeah,
have
sure.
strings that wind
Yeah.
around an extra dimension, and depending on how many times you wind it, the string will be more massive. It will have more
Yeah.
energy.
Yeah.
So that's one example.
That's a close decline.
Uh, but I think there are actually some real life example in condensed matter physics.
Yeah, like people might have seen these YouTube videos about quantum levitation, where they take these like discs and super cool them and send them spinning on a track. What's keeping those discs on the track is literally vortices with a defined winding number that are literally like stabbing like needles from the disc to the track and keeping on there.
Yeah, I
So
guess
there's like,
that's
yeah,
yeah. So I think vortice is another example. So if you have some twist
yeah.
in, I don't know exactly what's the best way to think about it.
But it's a
Uh,
stable configuration. And the stability of that configuration is what makes quantum levitation possible.
yeah. So basically, it's the idea that if you have sort of a twist in a whirlpool, I guess in water. Um, of course, water has dissipation. Vortices will eventually go away, but imagine you don't have dissipation. You have some twist in like vortices in a pool of water. That vortices will persist forever, basically, until it hits maybe a vortices that spins the other way. And when you combine
Yeah.
them,
And
they will disappear.
anti-vortice.
Yeah, and I think a good analogy is also like, what is it, like like haircuts. Like we have these, I don't know how many. Each person has like a little. I think you can have one.
Spiral.
What do you call those things?
That's spiral, yeah. I don't know. What's your winding number?
I don't know if they call a winding number, right? There's
That's
some topological thing about how many spinny things you have. No matter no matter how you cut your hair, unless you cut it like a hedgehog, like you're gonna get you're
hedgehog.
always gonna get one or two. Like that number doesn't change. Yeah.
Yeah.
So oh, okay. So the next thought is let's say so physicists study these topological objects. Then what's next? Like what are
Yeah.
the
So it's
results?
funny, like I feel like this whole Ed Witten program, it was kind of like a gift from God. Like we happen to have this guy named Ed Witten who just happened to figure out this way to get at some exact answers when the rest of us are just struggling to get approximations. But it's not like a recipe. It's like it almost seems like it's a one-off. Like uh you know, this program was successful for many years, but it has its limits. There are other attempts to try to get exact answers out of physics, more modern attempts. Um, but it really just feels like reaching around like a blind person in the dark. Like we don't have any
But
handle for how to do this.
but can we talk about some of the real life physical phenomenon that have topology in them? Like what are some
Like condensed
example?
matter stuff.
Maybe more closer to particle physics, right? Like I think that some of the forces actually have these topological things that people didn't realize before. I think.
Yeah, yeah. The idea of like vacuum decay. So people might have heard that there's some chance that our universe might dissolve in the near future. Um, this is related to this winding number. The idea that our universe might jump from a configuration with one winding number to another that could be catastrophic. But people might have heard of that.
Right, and that would be pretty violent, right? That would not be. a
Yeah. Does
perturbation
that
at
come
all.
okay?
And I think basically that's a sort of phase transition. It's almost like a
Yeah, it's
tone.
actually cool how it worked too. It would start in one part, and it would literally be a bubble of death that expands across the universe.
Well, and I think to be more specific, there are actually topological things in the different forces. I think what you mentioned is it the electroweak force or
Yeah. I think the false vacuum, the Higgs false vacuum decay.
yeah. Well, I don't know if that's exactly topological. But I think it's worth mentioning that even though we just talk about different winding numbers, quantum physics actually throws a wrench into this
Yeah.
because classical physics tells you that hey, if you wrap your rope around once, well, that's the end of story. You wrap your rope around once,
Can't unwind it.
you can unwind it. But quantum physics has this interesting property that you can be in a superposition. So it
Well,
means
anything
that
that can happen will happen.
so then is it true that you can be in a linear combination of having winding number 1, winding number 2, and different winding numbers,
Yeah.
right?
And so we come back to perturbation theory.
Yeah. So I guess it's sort of this interesting thought that even though there are different islands in the space of theories, because of quantum physics, we don't just live in any particular one of them. We actually live in all of
All
them,
of them.
right?
Yeah, at the
So
same time. We live in a mixture. And so this is really the kind of the upshot to this whole thing, right? Like, so we start with perturbation theory, where we have this picture of like particles that have high importance, and we build up the answer approximately by calculating the most important particles and ignoring particles that don't really have much of an effect. And then we try to go beyond perturbation theory by defining topology of these different sectors categorized by different winding numbers. And then we find out that because of quantum mechanics, we have to add up all these things anyways. And so there's actually this deep duality, this connection between the particles that we define topologically and the particles that we define perturbatively. It turns out that in a lot of cases, there's an exact equivalence between the two. And so,
yeah, I think
like
I
a
think
lot of
the
things in physics.
I think the exact equivalence is only made exact in string theory, right? I think there's even I forgot the name. Is it called S duality or maybe I misremember?
Yeah, I think it's S duality. Yeah.
Yeah, it's basically
T
saying that
duality is the radius of the size over inverse one.
is that right?
Yeah, T duality is like radius goes to 1 over radius. S duality is the one you're talking about.
Maybe it's T duality. Okay, well, don't take my
No,
word
it's not
for
T.
it.
It's not T. It's S.
Okay. Yeah, but just for some context, like why is string theory in all this topology thing? Because in the definition of string in the definition of string theory, we literally sum over all the possible topology. I think that's like string theory 101 if you would take a
Well, that's
graduate level
quantum theory.
course.
That's quantum mechanics 101. You just sum over every single possibility.
Right, but I think string theory is one of the first one to realize that hey, like you have to sum over topologies.
Topological sectors, yeah.
Yeah, but
Yeah.
yeah. So for those of you who are unfamiliar, like string is a a string is it's a one-dimensional object, right? But string over time will trace out a sheet. Like imagine a string moving, and you kind of what's the word? Like you do some motion capture, and you take a long exposure video of a string. It will trace out a sheet of paper, right? But actually, that sheet of paper can have very intricate structure. It might have a hole in it. It could form like the surface of a donut. It might be something like a sphere. And string theory is a quantum theory. So to define it, we have to sum over all the possible configuration with all possible different winding numbers, different holes, different handles, all the different topological stuff. I think that's probably one of the first example of.
Yeah, definitely.
Yeah. And indeed, in string theory, particles that have windings can be related to particles that just have more energy, more wiggles. So wiggles and winding, I think, become equivalent, which is
Yeah.
almost a little bit shocking, right?
No, it goes back to this duality. Like, we try to go beyond perturbative physics and we define these exact objects, but then we find out we have to do perturbations on these objects.
Right. So I guess the obstacle in one view, these cliffs and islands, you know, from another perspective, in string theory, they become, I guess with the right tools, you're able to cross them, right? You're able to climb the mountain, cross the ocean, and then just combine the theory all together.
Yeah.
And with quantum physics, it's actually all melted together.
Yeah. So I don't
Okay.
know. I think that's a good like this is really, I think for me, is like kind of the upshot with this whole discussion, right? Is like we try to define these exact objects, and then quantum mechanics forces us to sum an infinite number of them, and we're kind of back where we started. But we're left with this amazing insight that these sectors of the theory that we thought were unrelated are actually intimately related and may actually be equivalent.
Yeah, and I just want to remind the viewer that even though a lot of our discussion is hypothetical, these are real physical phenomenon. Like the strong forces, actually, it was discovered that there are different topological sectors. These are called, is it instantons? What are they called?
Yeah.
Basic, yeah, basically, it's telling you that the vacuum structure, it's a mixture of different winding numbers, and over time, when the universe was created, you can go through different phase transitions where dramatic things could happen. And I think in condensed matter, in condensed matter physics, this is way more ubiquitous, like superconductors, quantum dots, things I'm not as familiar with. People use that sort of technology.
And go on YouTube and look up some videos on quantum levitation if you want to see the power of vortices with exact winding numbers. It's pretty cool stuff.
I think also there are some recent Nobel prizes on topological insulator, for those who are unfamiliar, and that is also Princeton. So yeah, and literally using the power of topology, people were able to identify new exotic phases of matter, and then those might supercharge the technology of tomorrow. They might be the basis of quantum computers of tomorrow. So I know we're almost time's up. Any closing thought, Mikey? Insights?
That's my closing thought. I mean, it's been kind of a trip, going through physics, and like when we enter into our study of physics, we only think about perturbation theory. We only think about approximate answers, and then once you get to like the later end of your education, you start being exposed to these attempts at exact answers, and you start to see that it makes the whole game a lot more interesting.
I think for me, it's also to highlight that you think you know, but you don't. Like people, it's like people back in the days in classical physics, they thought, like Newton and is it Poisson and those
Kelvin famously said that the physics is done.
Yeah, we thought that all there was just particles moving around, and then quantum physics. Yeah, and then quantum physics throws an entire wrench in this whole idea. Yeah. And now, we thought, perturbation theory has solved everything that we need to know about theoretical physics. But, well, guess what? You can't answer all the questions. And I bet you, I'll probably bet good money on that we still don't have the full picture. I bet you that there's definitely more even beyond topology, beyond perturbation theory, and beyond all the tools that we have. So
it just feels like a taste of the truth, right?
Yeah, it feels like it's actually way bigger. Like we're not even.
Like you're just getting a small taste of it. It's a small taste of the truth.
Right. So hopefully, maybe in the future we'll we'll uncover some more islands and mountains that we couldn't reach even using
Yeah, and
topology.
the minute that anyone does, you'll hear it first here.
All right. On that note, well, thank you everyone for joining us, and see you all next week.
Good night.
Bye bye.
That was better.